In section 8.1, we're going to begin a preliminary theory of linear systems. So we're familiar with, from algebra, a system of n equations and n unknowns. And what we're going to have now is a system of differential equations. So we're going to have a condition on a function that's called the function g, or maybe the function solution should be called f, such that we want the derivative of the function with respect to the x1 variable with respect to time to be equal to some prescribed function. Its derivative with respect to the x2 variable will be some other function, etc. And these are all kind of derivatives we'll be taking with respect to time. We think of each component function, x1, x2 up to xn, as being dependent on the variable time. And the t variable can also be a part of these derivatives as well. But in general, what we're going to see is we're going to have n equations, and this is going to form what we call our first order system. Notice that in terms of the order, all of these derivatives are going to be the first derivative. Okay. When we write these functions g1 through gn above is linear in the dependent variables x1 through xn, we get what's called the normal form of a first order system of linear equations. So for example, the very first derivative dx1 dt is going to be equal to some coefficient of t times x1 plus some coefficient of times t of x2 up to, we could have some coefficient times the xn term plus, in addition, potentially some function of t as a part of this. The same thing could be true for the derivative in the x2 variable. It could be some component function times x1, component function of t times x2, up to some component function of t times xn, plus possibly a function of t, all the way down to the tth derivative of the x to the n variable. Again, it could be a component function of t times x1, up to a component function of t times xn, plus presumably another function of t. Okay. We will just kind of simply refer to this as being our linear system, and we'll see in a minute, especially when we get to the matrix notation, that we have the notion of a homogeneous linear system. The linear system itself will be homogeneous when all of these f of t functions are going to be equal to 0. Okay? If you have one non-zero component function fi, then we will refer to that as a non-homogeneous system. So very similar to the definitions we had previously, but now applying to these systems. Okay. What we're oftentimes going to do is we're going to invoke and use a lot of matrix algebra to help us write our linear system. We're going to let x be the column vector x1 of t, x2 of t, all the way down to xn of t. The a of t is going to represent these component functions. So across the first row of this matrix, you would have all of the component functions that were involved in the derivative of x1 with respect to t. So just the component functions go here. Similarly, in the second row of our matrix, you're going to have all of the component functions that involve the derivative of x2 with respect to t. And then all the way down the nth row of this matrix is going to be all of the component functions that involve the derivative with respect to t of the xn term. And then we form a separate column vector for the f of t component. The vector f of t is simply the column vector that consists of these fi functions, which would be the functions of t that are present in each of these derivatives. So it's f1 of t, f2 of t, all the way down to fn of t. With these definitions, we are now able to write our differential equation in the following format. The derivative with respect to time of this column vector is simply going to be the derivative of each component of this column vector. So the derivative with respect to t would be dx1 dt, dx2 dt, dxn dt, which is exactly the same thing we have over here on this left-hand side. We then have our coefficient matrix, this is the A matrix, times our variable matrix. And if you recall how matrix multiplication works, we would take each element in this column, multiply them correspondingly to each element here, So you'd have a1 1 of t times x1, then plus a1 2 of t times x2, plus dot 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 dot, plus a1 n t times xn. That would give us this part of the first derivative. And then when you take that result and you add it to this first component here, that would give us this complete first equation. More compactly and more concisely, we can write it as follows. So this left-hand side, this is the derivative of our x matrix. So we're going to denote that as x prime, always keeping in mind right now that that derivative that we're writing is with respect to t. This is equal to our our n by n matrix A times our coefficient matrix, our variable matrix x, plus f. If we have a homogeneous system, then we know that all of these f component functions would be 0, and therefore adding this column vector to ax, if you literally had the 0 column vector, it would simply provide us with ax. Let's get some practice with this. In example 1, they ask us to write each system in matrix form. If we look at the first system, it's as follows. We have dx dt equals 3x plus 4y, dy dt equals 5x minus 7y, and in general, we're hoping to write it as x prime equals a times x plus f. Now we're already calling this x comma y, so that's already kind of our column matrix. So it's going to be x prime equals, for the matrix A, remember that's just the coefficient. So this is a 2 system, right? It's got 2 equations in 2 variables x and y. So our A matrix is going to be 2 by 2. And literally you're just writing those coefficients. It's going to be 3 and 4 would be the first entries in row 1. In row 2, coming from the second equation, we have 5 and negative 7. And right now these are just constants, but keep in mind that generally they could be functions of t. And now that's going to get multiplied by our vector matrix for the variables x and y. So we have x. And notice there isn't really anything in terms of a function of t that's being added to these. So explicitly the f1 of t would be 0. The f2 of t would also be equal to 0. And so that matrix f this time is a 0 matrix, so we would not need to write it. So this would be our matrix equation for this one. X prime equals 3, 4, 5, negative 7 times the variable matrix x. Very similarly, let's look at the next one. In this one we have a 3 by 3 system, so we have 3 derivatives in the variables x, y, and z. Let's let x be our column vector. We again want to write it as x prime equals, in general, ax plus f. So it's going to be x prime equals, let's start by writing out the matrix A. If we go ahead and kind of go across the first row of coefficients, we have 6, 1, and 1. So that's going to be the coefficients for our first column, for our first row I should say. Now this part here is a t term. So that's the thing, and if you want to, you can write that now. That's going to be the entry of f1, the first row of f1. From the second equation, the coefficients are 6, 7, negative 1. Excuse me. 8, 7, negative 1. Like this. And now we have a term here as well that involves t. So 10t will be the second row of our f matrix. And then lastly, the third row, the coefficients are 2, 9, and negative 1. And we have a 6t term. So this would be the expression for our differential equation system written in matrix format. Okay. Notice too, again, you got to kind of pay close attention, making sure that they're written in standard order. If you had one of these variables or one of these terms that was missing, then of course you would want to kind of plug it in here with a 0 coefficient. The next thing we're going to discuss is what we mean by a solution vector. A solution vector on an interval I is any column matrix x equals x1 of t, x2 of t, down to xn of t, whose entries are differentiable functions and satisfy the system on the given interval. Okay. So what these are, so it's a column vector, all of whose functions are differentiable, and again, when you plug that vector into our differential equation, it's a vector x, such that it would make this expression a true statement. Okay. We would typically say that the solution vector is equivalent to n scalar equations, so we kind of get like these n different equations. x1 equals to phi1 of t, x2 equals to phi2 of t, up to xn, which is equal to phi n of t. And these can be interpreted geometrically as a set of parametric equations of some space curve. For certain low-dimensional cases, we can actually graph these things. And in the important case, n equals to 2, the equations would represent a set of parametric equations in the plane x1, x2 plane. So kind of think of it like, usually if it's x1 and x2, we would call it the x variable and the y variable, so it would be like the xy plane. So these would be things we could actually graph and look at what they would look like. And it's common to call that particular curve a plane, a trajectory, and to call the xy plane in this case, or you could call it the x1, x2 plane, is referred to as the phase plane. Okay, and we'll come back to that a little bit later to kind of go into more depth with this. And we'll actually graph a few trajectories to kind of see what's going on. Ultimately, the goal will be able to find these solutions on our own. So we ultimately want to be given a system of these differential equations. We would like to be able to find the column vector solutions. But let's start with example 2. We want to verify that on the interval negative infinity to positive infinity, that the vector x1, which is 1, negative 1, e to the negative 2t, which if you just kind of multiply the e to the negative 2t in, it's a scalar function, would provide us with this column function, e to the negative 2t, negative e to the negative 2t, and x2, which is 3, 5, e to the 6t, which as a single vector is 3 e to the 6t, 5 e to the 6t. We're asked to show that both of these are solutions to the system written in matrix form, x prime equals 1, 3, 5, 3x. Okay, so let's start by showing x1 as a solution. So we have our x1 vector, which is e to the negative 2t, negative e to the negative 2t, and we want to plug it into this differential equation. Well, one of the things we're going to need is the derivative of this, and we said that to find the derivative, all you need to do is differentiate each element of this column vector term by term. The derivative of e to the negative 2t is going to be negative 2 e to the negative 2t, and the derivative of this term is going to be a positive 2 e to the negative 2t. Let's go ahead and plug them in. So the left-hand side would be our negative 2 e to the negative 2t, 2 e to the negative 2t, and we're checking this, is this going to be equal to 1, 3, 5, 3, that 2 by 2 matrix, multiplying to x, 1, which is e to the negative 2t, negative e to the negative 2t. So we're asking this question, is x1 prime equal to a times x1? Well, to do this, the only thing that remains to be done is we need to multiply this right-hand side. This is a 2 by 2 matrix times a 2 by 1 matrix, so we can do this. One of the things you might recall from matrix algebra is that to multiply two matrices together, if one's m by n, the other one must be n by k, so these two numbers have to match, and if they do, then the result will be a 2 by 1 matrix. So this is negative 2 e to the negative 2t, 2 e to the negative 2t. Let's check this right-hand side. We start by multiplying this first row by this column. We do 1 times e to the negative 2t, and then we're going to add 3 times the second entry, which is negative e to the negative 2t. That's going to be the first row of that matrix. And now we take the second row and we multiply the second row by that column. That's going to give us 5 times e to the negative 2t plus, now we have 3, this 3, multiplying by the negative e to the negative 2t. And let's tally them all up. We have a positive 1 e to the negative 2t, and a positive, so this would be a negative 3 e to the negative 2t. So altogether that would work out to be a negative 2 e to the negative 2t. And then this is a 5 e to the negative 2t. This would be a minus 3 e to the negative 2t. So those will combine to give a positive 2 e to the negative 2t. And these two vectors are equal to each other because their individual components are equal. So that shows that x1, which is e to the negative 2t, negative e to the negative 2t, is a solution to this differential equation, this system of differential equations. Let's now go ahead and do the same thing. Let's try to check to see whether or not x2 is also a solution to this system. So to see whether or not that's going to be true, we need to check and see, is it true that x2 prime, is that going to be equal to a times x2? Well, we have x2. x2 is 3 e to the 6t times 5e to the 6t. Let's form x2 prime. This is going to be equal to the derivative of this function here. That should give us 18 e to the 6t. The derivative of this one here is going to be 30 e to the 6t. And now let's plug it into this differential equation. x2 prime is 18 e to the 6t, 30 e to the 6t. Is this equal to a, which is 1353 times x2, which is 3 e to the 6t, 5e to the 6t. And this left-hand side isn't going to change. And all we need to do is multiply out the right-hand side. We start by taking the first row times that first column. That's going to give us 1 times 3e to the 6t, then plus second row, second column times this term, 3 times 5e to the 6t. We now move down to the second row, multiply it by that column. That's going to give us 5 times 3e to the 6t, plus now the 3 times 5e to the 6t. We can go ahead and tally those up. This will be a 3 plus 15 will give us an 18 e to the 6t because they're like terms. And here we have a 15 and another 15, which will give us a 30 e to the 6t. So again, these two vectors are equal because their components are equal. So that also shows that x2 is a solution to this system.